So 250 times the cosine of 35. I see when I look at my calculator, I missed the 2, so I get to type it again. I got 204.8. And for our purposes, I'm not going to worry about rounding right now. $204.8. Sheesh. Come on, man, wake up. What's the matter with you? Are you broken? But that choice right there could cause me to get the answer wrong in the back of the book. Do you understand why? Because remember, we got to round to 3 digits ultimately, and maybe I'm rounding that too soon. Does that make sense? Maybe I'm rounding it too much too soon. So if I look in the back and I see that my answer is the same as the back, but just a little bit of rounding, I'll kind of tell myself, oh, I should have carried it up a little further, and I won't do anything else. Like that's what as far as your homework is concerned. But learn from it. Don't redo it, but learn from it. And then 250 times the sine of 35 is 143.4. So now I know what those links are. And so, and I think this is where you were going. If I was to kind of put these in the picture, then this is the 204.8, and this is the 143.4. Do you agree now? And this is what I think you were just saying. Do you agree that the 143.4 is the z now, but we actually don't know x and y? That's going straight down. So that's actually the force that is parallel to the z-axis over here. So that's actually my z. I'm kind of done with that. But what's 204.8? Is that x or y? Yeah, it's actually both. It's the hypotenuse of the x and y. We don't know either x or y, but we know the hypotenuse of the x and the y. You see how it's like if you can't picture what they drew there, you got no chance of getting this question right. And it's very hard to see. So those right angles I threw in there, huge. As far as a test was concerned, if I had a question like that and you came up and said, this is what I think I'm seeing here, is that what I'm seeing? I'm totally going to answer that question. Because this is not a like visual, this is done. Like in the real world, you'd actually have the rope, you know, and you'd be able to turn it in your hand. You might have a 3D model so you could flip it around and go, oh, I see what's going on. But it's super hard to see in 3D. Frankly, the drawing is excellent. Like I couldn't do even half that good. Even with the computer, that's about as good as it could get. Yeah, it's entirely because this angle, thank you for speaking up. Notice how I'm being very careful to draw this line parallel to this line because that's what X is doing, and this line parallel to Y. Like that's the 90-degree angle. So this triangle is laying flat on the table, it's flat. And because this is a 90-degree angle, then I know that must be the hypotenuse across from it, even though it doesn't look like it. As I said before, that angle looks way less than 90 degrees, whereas this one down here actually looks like 90. If you screwed that up, then you're going to get everything wrong. Now, if I was able to stand over the top of it, I would go, oh yeah, I can see it now, right? But that's really hard to see. So I think I'll squeeze that in over here. So if I redrew that red triangle over here, where this is the 204.8, looking down on it now, looking straight down from above. And again, notice I know that that's 25 degrees. And so that 25 degrees is that angle right there. So I can fill that in over here. And so what was actually one of the sides of the previous right triangle is now the hypotenuse of this right triangle. So now I can say the same thing I said before, which is, well, wouldn't this side here be 204.8 times the cosine of 25? And this one over here would be 204.8 times the sine. This class is small and we're friends. Like, don't even raise your hand, like start talking when you immediately, even if you're not, if you think, I wonder if this is a dumb question, I'm going to wait a minute before I ask it. I'd prefer you don't. Clarify, even if you're just clarifying your understanding. So 204.8 times the cosine of 25. I got 185.6. And 204.8 times the sine of 25, I got 86.55, or I'm going to call it 86.6. Remember, everything I'm writing here, I'm going to post after class, so you can strike a balance between writing yourself and paying attention. Okay, so now I actually have all of these lengths. If I come back and add them in here, 185.6 is this length. I'm going to draw a little cloud around it because these are the actual X, Y, and Z. I broke that 250 Newton force into 3 components now, X, Y, and Z. And lastly, this one over here, 86.6. Everything I did was to come up with those 3 numbers. Do you see them as parallel to the X, Y, and Z axes? That's why it's important I found those lengths. Again, I say lengths in quotes. And can you also see which ones are positive and which ones are negative? Because remember, I did this as right triangles. I didn't rename the angles. Like Connor pointed out, maybe that 35 should be negative. Well, I just went with the pictures that I saw. So would you agree that the Y is positive because it's in the positive direction? What about X? Is it positive or negative? Yeah, so if I start from here, I went positive Y and then positive X and then down Z. I went the opposite direction, so that's actually negative. So would you agree that my force 1 is positive X 86.6, positive Y 185.6, and positive or negative Z, I'm sorry, I didn't realize I was writing so small, 143.4. Should that have a label on it, that vector? So because of the fact that I wrote it there with those brackets and commas, I don't need the IJK because we're used to seeing that as X, Y, Z, well, at least X and Y. So that's in alphabetical order. But I could have just as easily have written this as 86.6 I plus 185.6 J minus 143.4 K. And it is kind of a good thing to, even put a little vector symbol over the top of that. Go ahead, Ian.
That's the Cartesian vector.
Exactly. That's the Cartesian way of saying that. Rene Descartes is the one who was sort of famous for recognizing that a graph could basically, one point could hold 2 numbers simultaneously is the idea there. So those are both great. They're both fine. The key is just don't mix up which one is which. Does that make sense? That's all that actually matters here. And out of laziness, I like the top one better just because I don't have to write as much stuff. As far as units, what were the units of these numbers? Newtons. And so in the book, you'd probably see an N behind this, just telling, hey, by the way, these are all Newtons. Or you could even put Newtons at each one of them. But the key is it makes sense that I just broke down that complicated force in some weird direction into its X, Y, Z components. And now if I can do it again to the other one, then all I have to do is add them and I'm done. So it's actually no different. It's just painful in 3 dimensions. Does that make sense?
So I get home and I put my 90 degrees in the wrong spot.
Yep.
I don't know why it's not working.
Yep. And that's exactly why I assigned the questions that have the answers in the back. So you need to know that something's wrong. And the other thing I would do is don't try to write really slowly and clear, waste a lot of paper. You should be using engineering paper and wasting a lot of it so that you can bring it to me and say, where did I go wrong here? Because you need to fix your thinking. Don't just wad it up and say, I'll try it again. We should look at everything you did and go, what went wrong here? Now, there's something really cool to check your work here. Oddly, the Pythagorean theorem actually still works for this. Does it make sense that if I took 185.6 and squared it, and 86.6 and squared it and added them together and square rooted it, does it make sense I'd get 204.8 if I didn't screw up? But then isn't 204.8 itself actually the sides of this green triangle down here? So if I took that and squared it, which remember actually was these two squared and added together anyway, and then I squared this and added it and squared it, wouldn't I get that? So actually it turns out if you take your three black numbers there, square them, add all three of them together, square root it, you better get 250, or you choked. Now, am I gonna get 250? Notice my tone of voice?
You rounded it, so it might have some rounding.
Yeah, I'm not because I rounded, but I'll get close, right? So that'll tell me, hey, cool, everything's all right. The reason you get paid as an engineer is because you're the one checking the work. In this class, I'm going to check your work and help you when you're wrong, but that's like, this is the last time, like from then on, it's like, you're the one that's got to check your own work. That's why you have a stamp. That's why you're paying you all the money. Someone's got to be the final person that loses their job and gets sued, right? Someone's got to be last, and that's what you're studying for and hopefully going to get paid a lot for. Okay, what about the other one though? Woo, man.
I can't tell whether that's going in the positive or negative X direction.
Yeah, honestly, in one respect, it could be argued that the second one is even worse. But do you see what they've done? What are those measurements? I've got three angles here that they're, what color haven't I used? Orange. Three angles here. What are those measurements from? They're all measured to the vector itself, the force, the rope that's pulling on it. But what are they measured from?
From the plate or whatever that is.
Look at the other end of the arrow. From what? Yeah, from X, Y, Z. They're actually measured individually from the axes. And this is super weird. So let's go over to the corner of the room here. So if this is the origin down here at the floor, and I'll call that X and that Y and this Z. And let's try to picture like, what would you call it if I went in the game to that little box on the ceiling back there? So I'm down here in the corner and I'm like, I'm gonna fly off in that direction. So it's literally an angle that is measured. So we said this was X, it's literally measured like not even in any of the planes. You see what I'm saying? It's like from there to there. So that angle is not X, Y, or Z. It's like running through space. It's some totally weird angle. So to me, that angle looks like maybe about 60 degrees right there. And then over here, that's a little smaller. Maybe that's only like 30 degrees. And then from here, all the way down to there, maybe that's like 45 degrees. So those angles are actually in a totally, they're not in any plane that you can recognize. And therefore, it's extremely hard to tell where they're going. Now, the really cool thing about this, though, is you don't have to do anything other than stick those angles into the formula, and that helps the answer. So that's actually easier. So that first method was as transverse azimuth method, whereas this method is actually called coordinate direction angles. Again, I only say that because you might see it in the book. But coordinate direction angles, I guess that makes sense as a name because it's actually measured from each of the coordinates, the X coordinate, the Y coordinate, the Z coordinate. Now, of course, one of your thoughts should be, are those positive or negative or what the heck? But what do you notice that every one of them is measured from positive X and positive Y and positive Z? That's actually not an accident. Because they're measured from positive X, positive Y, positive Z, then I can just use those angles as they're given. And by the way, notice the one from X is 120 degrees. Can you visualize that? That's basically saying, whoa, that's a long ways off from positive X. It's like, wow, 120, it's like way over there.
So it's like Y are 90 degree almost.
There isn't one. That's the problem. There isn't any 90s here. You're in a world of hurt with this one.
Because what I was trying to do is think of it as like if 90 was our y-axis and we're like 30 degrees to the left of negative x. Is that a bad thought? The
problem is the plane that's in is not along the x-axis. It's not like if this is the x-axis, it's not like you went 120 like this. It's like you went 120 like that. That's the problem. It's not even, you're looking at it and seeing it as going along X like this. It's not doing that. So it takes 3 angles in order to define where you're going here, but you can't, like the picture is almost no help. Like it's worse. Like don't even give me a picture because I can't even make any sense of it. So it is actually really cool if you can kind of pull this out, but take a look at your note sheet that I gave you the other day. I'm sometimes savvy enough to actually display that note sheet here.
So if you just take like, I was gonna say like Joey wrote, but then I was like, oh wait, we have to actually know the answer to plug in Joey wrote, but do we? Can we just use those angles like you said, like 400 cosine 120?
No. Well, kind of. So here's the payoff. Where did that go? I need to pull this up on my iPad, but I just didn't think about it before class. So I have to do it this old school way. First of all, notice this says magnitude is, and do you see how the 3-dimensional Pythagorean theorem, that's what we just checked a second ago. So the Cartesian vector that we're after, remember we just got one of those a second ago. There's an X, a Y, and a Z component to it. And if you square all those and add them together and square root it, that'll actually give you that 250, that magnitude we just got a second ago. But then for coordinate direction angles measured from each respective, what's that say right there? Positive, that's very important. Measure from the positive axis. Now, fortunately, the book is not going to screw with you there. It's not going to like give you, haha, I gave you the negative. It's supposed to be negative. Like it'll, but just notice in the drawing, it'll always be measured from the positive. Notice we have kind of a, I don't know, for a bit lack of a better word, kind of a mindless formula now. So this is actually better. And it should make sense to you because isn't that how we found, since it's measured from the positive, let's do it this way. If this is your angle right here, isn't this side next to it, isn't this cosine right down there? Isn't that cosine of the angle is the one that's adjacent to it? And that's kind of why it's cosine every single time, because we had the positive, we're measured from the positive axis. Let's see if we can picture this a little bit. Basically, this is the value that we're after because we wanted the X coordinate, right? So in our problem, I forgot, was like 400 newtons was our hypotenuse. That was our magnitude for A. We're after this one. And we actually know what the angle is down here. We know the angle from the positive x-axis is this. So there's like 1, 2, 3 unknowns here, but we know this one and this one. Then we're going to be able to find that missing side. The key is that side, the X would always be adjacent to it. Let me see if I can show you that in the picture.
So going backwards from cosine to the other side, right?
Yeah, now the cool thing about 120 is if it's supposed to come out negative, it will automatically. That's what's cool about 120, because 120 does not live in a right triangle, but 120 does exist in 360 degrees, and this is why you took Math 112. And you might, even when I teach Math 112, a lot of times I'm always kind of insulting the fact that it's like, what do you mean cosine of 120? It doesn't make sense. Trig is right triangles, and there's no such thing. And so I spend a lot of time trying to help students make sense of that. But the cool thing is if I just take the cosine of 120, it's going to come out negative on its own if it needs to. And you can appreciate that, if I went 90, then I'd be straight up. But if I kept on going, isn't that going to take me away from the positive x-axis? Doesn't it kind of feel, even though I don't really know what direction it's going, doesn't it feel like it should be negative? So let's use those formulas to get force 2. Well, not so much force 2, but the vector version of force 2, right? So let's see, I have alpha according to this formula, and you may recognize on your note sheet, those are Greek. Let's see, alpha, beta, I think it's gamma, alpha, beta, gamma. So alpha goes with x, and that is equal to the inverse cosine of the x, the f2 of x, notice what I'm labeling that, over yeah, I was trying to decide if I should just put the have you seen that symbol for magnitude? Yeah, you should have in Math 112. The magnitude of that force 2 vector. Remember, there's a difference between magnitude, which is a number. Magnitude is 400, whereas the x, y, z components are the vector version of the exact same thing. So let's see, in our case, yeah, we know this angle is 120 degrees for x. And we know this magnitude down here is 400. By the way, what I'm doing there is kind of a cool thing to do, where you actually write the formula out. But I didn't erase it and write something over the top, but it kind of helps me to stare at it. I haven't really lost. I can still see through the line that I made, but also I'm knowing I'm replacing that. So then if I move the cosine to the other side, then isn't that what I have? And so I end up taking, what am I really doing? I'm doing exactly what we did a while ago, which is just taking 400 times the cosine of 120. It's not like I actually have to write all this out. It's just cool because it's like cosine every single time. So last time we had to think because we drew a picture and sometimes it was sine and sometimes it was cosine. Just take 400 times the cosine of that angle and you got the x coordinate. Like that's all you actually have to do here. So even though visually this coordinate direction angle thing is sort of hard to visualize and so forth, mathematically, man, you could just plug it in and get your answers. It's like super simple. So 400 times the cosine of 120. Oh, look at that. It did come out negative and it came out exactly 200. And I have a little system that I use for myself that you're welcome to steal, but I put little clouds around stuff that's important because I'm all lost in my work. And then I put a box at the end and it's like, this is the answer. And this is actually the answer that I was supposed to end up with. And that's when I look in the back of the book and see if I got the dumb thing right. But this allows me to kind of look back and not get as lost. Colors are awesome too, if you have any way to do that. I'm now addicted to the iPad thanks to a couple of years of having to use it. So there's the x. And so if I just kind of follow that logic, then that means if I took 400 times the cosine of, let's see, what's y? Y was 45 degrees. Also notice the subscript thing. You can kind of write this however you want, but there was a force 1 and a force 2, but then there's also an x. And so it's kind of like I have 2 subscripts for this. That's actually great. 400 times the cosine of 45 is a positive. Does that look positive? Is that thing aiming in the positive y direction? I think you can see that that's the case here. But I can't visualize this 282.8 that I just got at all. 282.8. That's an important number.
Does J belong behind that value?
Yeah, right now I have an x and a y that's keeping it straight for me. But yeah, if I choose to write it in this way that we did right here, then I'm going to come back and put an ijk. If I choose to write it in this bracket form, then I'm just going to make sure I get them in the right order. Because yeah, we got to get these in the right order. That's all that ijk means. That's all that parentheses and commas ever meant with ordered pairs is x is different than y. Keep them straight. Don't screw it up. And that's the same thing here. So then lastly, 400 times what's our angle there? 60 degrees. 400 times the cosine of 60 is force 2 in the z direction. Oh, they were nice to me there too. It came out 200 again, so I can actually say equals, not approximately equal. Notice I'm being lazy and leaving the label off, but I'll get that back in there later. So now I can say that force 2 as a vector is equal to, let's see, I'm going to stick with the bracket thing this time. So let's see, which one was x? X was 200, z, y was positive 282.8, and z was, well, they were all positive, weren't they? Didn't I screw one of these up? 200. This was negative, wasn't it? I screwed that up. The last one was positive. So now what this allows me to do is just add x with x and y with y. So if I say, what is, let's see, what do I call it? What were they asking me for? Force resultant. So all I have to do is add these. So I could say, now that that work is done, I could say the force resultant as a vector is force 1 plus force 2. So I'm looking at their x components, 86.6 and negative 200. Don't trust myself. Negative 113. And 185.6 and 282.8. Four 68.4. And finally, negative 143 and positive 200. Let's see, I can do that in my head. 56.6. Now let's take a second and stare at that. First of all, like, do you find yourself at a glance just kind of going, oh, that's interesting, well, that's gigantic, and that's really tiny. Can you see that in that picture up there? Those pulled together. Remember, you're trying to draw them head to tail, which is very hard to visualize. But it'd be like taking one of the vectors and putting it head to tail with the other one.
One's going up 45, the other's going, oh wait, no, one's going up 60, right? And then one's going down 35.
Yeah, so at a glance, the fact that one's going up and one's going down, does it make sense they're fighting against each other? That's why Z came out so small. Whereas what's happening in the Y direction?
It's going up.
Here's positive Y. Isn't this one pulling toward Y positively? And so is that one. So they're working together. That's why that one's so big. Now, it's not that I could know what those were, but it's the point is like that picture actually matches what I just calculated.
So Doug, if we wanted to confirm F2, those three components, 200, 282, and 200, put that in the Pythagorean theorem, and it should come out, right?
Yep. So I never checked that, but if you put 200, 282, and 200 into the Pythagorean theorem, you better get 400. So we should check that, right?
Yeah, it's square root, and then you add the square root of all, or add the.
Yeah, the best thing is to type a square root sign and then say 200 squared inside there plus 282.8 squared and then plus 200 squared. Just type the whole thing and I got 399.97. Oh yeah, cool. 400. So I didn't blow that. Now, are we done? Well, we are in the sense that we found the vector. We found the actual resultant vector, but it's listed in terms of its x and y and z. And that's great, but you could also turn it back into the world it came from. Like this came from the world of, because in the end, wouldn't you actually want to know the final magnitude? Like how many, we got 250 and 400. What's the final answer to this question? We don't know, but how are we going to figure it out? Yeah, same thing we just did, Pythagorean theorem. Notice this question is asking for two things, the magnitude. So we're going to have to Pythagorean theorem that last answer. And unfortunately, coordinate direction angles of that resultant force. In other words, they want us to tell, they want us to know where does it, which direction is that going? And I think you can appreciate that's important. Like you do need to know what direction it's going in order to figure out, as I said, what to do with the screws and the bolts. Just knowing it's got 900 newtons on it is not enough. You have to say it's pulling in this direction. No, it's pulling in that direction. I noticed the form they said is, they said coordinate direction angles, like the angle from each axis. They didn't say azimuth transverse, which is actually wonderful news, by the way. It's actually way better because we have that little formula, that inverse cosine formula that allows us to do this. So let's do that. And again, some of the symbols for this stuff, how do you write this? I need the magnitude of that vector. A lot of times you put two lines there instead of one, because if we use one line for absolute value, and so sometimes you'll see two. Some books won't, just put one, and that's fine. So if I take the Pythagorean theorem, You should already know this, but if I type exactly what I just said right there, I'm going to get it wrong in my graphing calculator. Do you all know that?
Oh, yeah, you need parentheses.
You know, you need parentheses around that negative because your calculator is going to square this first and assign the negative later. And so you'll get it wrong. You probably won't notice it, but that's why you look in the back and get it wrong. You should just be, you just say, I already know a negative squared is positive. Just leave the dumb negative out when you type it in.
Oh, wow. 457 with and 485 without. Wait,
Wow, so it's not very different. So yeah, we definitely wouldn't have been able to tell then, right? So yeah, roughly 485, is that right? And notice I was kind of lazy about units. I didn't include them all the way through this, and there's debate about that. I think Dusty is like really into units, which I think he's right about. But you have to think about them, but there's a lot going on. And so sometimes I'll go, okay, everything is in newtons. So I just know that when I'm all done, I'll be in newtons and I'll be lazy and leave it off. I'm very conscious of that, but I'm just not writing them down every time. Notice rounded to 3 decimal places. That's the answer I'd see in the back, even though it may be a decimal that's carried out further. And then lastly, the coordinate direction angles thing, and the formula that's on your sheet is actually made for what we're about to do right now, which is we need to know the angle, and the formula was written like this, right? It was written, this formula was designed to spit out that alpha angle, and that's what we need now. But now we actually know our force in X and we know the magnitude. So if I take the inverse cosine of that, it'll spit out the angle from the X axis that gives me. So
You put 45 on all this.
yes. So alpha is the inverse cosine of the X coordinate, which was negative, and you need the negative, divided by the magnitude, which we just now calculated. So notice we couldn't have found the angles first. We had to actually find the magnitude, or we wouldn't have had all the ingredients for a recipe. So if I take the inverse cosine of that, I get about 103.5 degrees. But you probably would see 103 in the back of the book because you're never going to see 4 numbers, but who cares? So that's alpha. The X coordinate is called beta, second letter in the Greek alphabet, also inverse cosine. But of course, that's 468. That's interesting. It's really close to 485, right? 468.4. I wonder what that's going to do. What kind of an angle is that going to spit out? I wonder if they're really close. Do you have enough intuition from basic trig if you were to think about this? We don't need to think about it. We have a calculator, but if it spits out 15.1 degrees, are you able to go, oh yeah, actually that makes sense.
What's cosine of inverse cosine of 1? Oh, it was closer to 90.
Yeah, think the unit circle. The cosine of 0 is 1 because cosine is the X coordinate. So the cosine of 0 is 1. Well, you're taking the cosine of a pretty small angle there, something that's pretty close to 0 degrees. That's why you got, I think I just said that wrong. The cosine, yeah, the cosine of 0 is 1. So it's such a tiny angle. That's why you got something so close to 1. And lastly, I think this is gamma, just to write it in the notes. This is the opposite. This is like a tiny number over a really big number. I wonder what kind of answer that's going to spit out. The answer is something pretty close to 90.
And that's the z-axis. So this is going like really steep, like upward.
Yeah. So just for the fun of it, even though this is not going to be fun, let's try to draw it just to see if we can pull it off. Maybe we shouldn't. This actually sounds like a bad idea. Because see, the problem is I can look at 103 degrees, but if this is the x-axis, do I go 103 this way or 103 that way? You see what I'm saying? It's like I have to know the other ones to even know what direction to go. So I'm sort of thinking, I don't think I can. I think I need some 3D drawing program where I can, dimension it and spin it around, turn it so I can see. Because like this angle right here, see how that angle is like 45 degrees, but if I turn it like this, it's 0.
Right.
But then if you're able to turn it, with the maximum I can see is when I'm straight at it, and then it's 45. And so unless I'm looking right at it, I can't see. That's just really weird.
I'm definitely gonna message Joe about home because I still don't understand the x-axis like what you're saying. It goes in like an angle.
Yeah.
I have respect for people drawing these diagrams like that.
Yeah. Doug, weren't you saying that you met a guy at a conference? Well, aside from the calculator guy, that someone could just draw from freehand like incredibly well.
Yeah.
Because that's how they had to do it.
I'm very, yeah. People that were kind of in the
Yeah.
pre-technology era didn't have a choice. Okay. So let's take a look at this one. That one's over there. Grab that one because I don't think I handed that to you. So this is the same question, fortunately. But kind of not. So what's the same about it? Well, it's the same because it has two forces pulling on it. Isn't that what we just had a second ago? Two forces pulling on it. And this is also metric, 560 and 700. But at a glance, at a glance, what did we have in the last figure that we don't have any of in this figure?
You don't have any angles.
Angles. That was asking me to read my mind. We have no angles, so it's like, what direction is this thing going? We don't have any way of knowing that. And this is just like what we did the other day when I said, you know, what direction is that going? And we said something like, well, 32 degrees. That's the direction that's going. And you're like, oh, okay, I get it. But didn't we also say that it was perfectly okay to say, doesn't that also tell you what direction that thing's going? Well, that's what's going on here. And that's not uncommon because in a sense, you might actually be able to build that. Whereas you'd be hard pressed if I hooked a rope to the wall over there and told you to pull it in the direction angles that we just had. It'd take a while to set that up. Does that make sense? Whereas if you have distances, and notice all of those distance measurements are parallel to the X, Y, or Z axis. And so you're being given, well, kind of like this, except for instead of 5 and 12 and 13, now it's kind of like 5, 12, 7, and 13. Like we got a three-dimensional drawing of that. So, so I've got to do the same thing I just did, because what is it asking for? It's asking for the magnitude and coordinate direction angles of the resulting force. It's actually asking for the same thing. Now, before we dive into this a little bit, notice how the flagpole is bolted to the ground down there. And this guy does a pretty good job of actually, you know, not just wimping out on some of the details, but you can appreciate if you did pull on the flagpole, as this is saying, in these directions that are hard to tell, like those bolts are going to get tested. And incidentally, can you tell which ones would get pulled out?
The far one.
Because if it's laying flat like this and you tip it, doesn't this side get pulled out and this one over here almost does nothing? That's actually true. It's not just how many bolts do you have, it's like which ones are getting ripped up. And so that's why it's so important to figure out what direction is this actually pulling, because ultimately that's going to allow us to figure out how much force is put on the bottom of that plate, and then we're going to be able to put the right amount of bolts and concrete in the ground to keep that actually from happening. So remember, we're always stopping short of the real answer that an engineer wants for this. But the question is, what direction is this thing going? So again, we got two independent forces. But from the last problem, of course, the figure would be out of control. But does it make sense for the way we just did that last problem? There could have been 10 ropes pulling on that, and it would have been the same thing. By the time they got 10 things dimensioned on there, we wouldn't have been able to see anything. That's why they stop at 2. But what's so cool about breaking it into X, Y, and Z, trig can take over, and I can figure this out. So I got a force of B and a force of C, and I kind of like the way that's labeled. As I said, get used to this kind of thing. If I was labeling this myself, I could have called that force B right there. I could have called it force AB, as though it's pulling from A toward B. That's kind of cool. And this one I could call it force AC because it's pulling from A to C. Or you could just not worry about AC, CA. But there's some things that can kind of help you a little bit. Okay, let's just dig in. So we got a force B and a force C. So I'm going to try to organize my thinking here a little bit for no good reason. I'm going to start with force B first, and I'm going to kind of highlight, hey, these are all the calculations I'm going to make about B. And I'm not even looking at A. And so let's see, what is B doing? What direction is it actually pulling? Notice it's emanating from here, just like last time the rope was pulling on that ring. But the question is, what direction is it going? How far in the X, how far in the Y, how far in the Z? Is that given? 6, 2, and 3, I agree with that. Notice the positive X, positive Y, positive Z. So from here, in the X direction, this is the X direction here, it's pulling this far. You agree with that? It's pulling that far.
And you just go straight to like correcting coordinates.
So that's 2. You agree with that? And then, actually, wait a second. I should do this up above. Well, remember this is, lined up with this. So then it's going this direction parallel to Y. It's going this direction in the Y. That's its distance in the Y. Notice that's a 3, but it's not 3. What is it? It's -3 because it's going the opposite direction of the positive Y. Does that make sense? That's important because if you get the negative wrong, then you're totally going a different direction. Because remember, we're going to have to add these together. And then what about Z? Yeah, down. And so you don't necessarily have to do these in order. In this case, it might have made more sense if I sort of went first here and I recognized, oh, it's 6 because that's parallel to that, but it's going down 6. And so that's -6. And then secondly, once it got there, then it went positive X, positive 2. And then lastly, it went here, -3. But that isn't in order, right? So it's like I got them written down now, but then I got to actually write them in order. So it's kind of like, I'm just making a note to myself. It's kind of like X was +2. That's kind of the direction it went. But what did we do the other day when we were talking about this? If this force was going in that direction, and it was say 900 pounds, then how much of that is X?
900 cosine of 12.
You don't have any angles, so you can't bust out any cosines.
Oh, yeah.
What proportion of it is, well, this?
Would that be, yeah.
Yeah, see how this is parallel to this? It's 12/13. So this force right here would be 12/13 of 900. It'd be 900 times 12/13. That's the proportion. So I need the hypotenuse is the point. See what I just wrote up there is a bunch of X's, but I also need the hypotenuse so that I can kind of finish this. Because remember, I have like a 3-dimensional Pythagorean theorem here. So I need the X direction divided by the hypotenuse. I need the Y direction divided by the hypotenuse, and I need the Z divided by the hypotenuse. And that's what I'll be multiplying my 500 or whatever the number was. So this is real important. You're going to see this a lot. Make sure you kind of find yourself going, yeah, that makes sense to me now. That's a proportion. Now, just to give you one more shot at understanding that, if this was the angle right here, would you agree that's cosine? Cosine of theta is adjacent over hypotenuse. Isn't that what we were doing earlier? Is taking 900 times the cosine. That's what you were trying to do a second ago, wasn't it? Like 900 times the cosine of whatever the angle was. But if you have 12 and 13, you already have the answer to what cosine of theta is. That's what's kind of cool about 12/13. That is cosine of theta. So you don't have to go get it. Now, if you want to, go inverse cosine of this and get the angle, and then come over here and take the cosine of that angle, and then you're going to get 12/13 back again. Like all that work for nothing. But that's what's kind of profound about this, is that's what trig tells you is the ratio of two sides of a triangle. Well, if I have all the sides, then I don't need any trig. Which again, I don't think is obvious. Well, how are you going to find the hypotenuse of this thing? you're going to square them and add them all together. Notice I'm being smart, not lazy, and taking out the negatives myself. 36 and 9 is 45, 45 and 4, 49. Weren't they nice to me? The square root of 49 is 7. So the hypotenuse is 7. So the force of B in the x direction will be 2/7 times, what was the force of B? 560. 2/7 in my three-dimensional right triangle. 2 is in the x direction. 7 is the ultimate hypotenuse. And they were very nice to me for picking 560 there, because 560 divides evenly by 7. It's 80, and times 2 is 160. So my force, I'm breaking 560 again into its three components. I just found my x component. Yeah, and this is Newton's, and I'm not ignoring that. I'm just not writing it down. Force B in the y direction. The y is -3. Does the negative matter in this calculation? Yeah, because when I get all done with this and I get 240, then I'll say negative, because it means instead of going that way, it's going this way, and that's huge. So the negative is really important there. And then lastly, the force of B in the z direction would be the z coordinate times 560. That'd be -480. So I can now report, and I'll do it the other way this time. I can now report that force B can now be rewritten as a vector as 160 I minus 240J minus 480K. I, J, K. At least they're in alphabetical order. They could have picked P, G, and S or something stupid like that. So 560 was pulling off in some weird direction. And now I've split it into its X, Y, Z components. Double check, 160 squared plus 240 squared plus 480 squared better be 560 or I blew it. So, mission accomplished. Force B is figured out. I'm going to give you a second to get ahead of me with respect to force C. Since my drawing is, my previous work is like over the top of force C now, I think I have to get rid of that stuff. But one thing I can't do on this is copy that figure twice. That would be nice. See if you can repeat that for force C. Ask me questions, talk to your neighbor, good job. Just make sure you notice the arrow is really important. The last problem went from A toward B. And that's why the signs were the way they were. So here we're going from A toward C. A is our start. B is the direction we're going. So we've got to get the negatives and positives based on that.
So with the x direction, 5, because it says 2. I'm trying to read. It's like, is it 3 meters plus 2 meters? Why is that?
Yeah, so basically it's kind of like this. I'm standing in this corner and let's say I want to go to that opposite corner over there, but I can't just go straight there. I have to follow parallel to X, Y, or Z. So I can do whatever one I want first, but I can first start by going, I think I'll go up to the ceiling. There I went Z, and notice in my case, that was positive. And then I think I'll go X next. And so I go that direction down the corner of the wall over there. And then I turn last and I go Y. And the question is just, are those positives or negatives? So, but you have to go from where you started toward the arrow. So the way I look at this is just, well, I got to start here. I'll do this a little better than I did last time. I got to start here. And the first thing it's very hard for me to see in space. And so the first thing I'm going to do is go down to there, which is -6 in the Z direction. Remember, here's my destination, right? That's where I'm headed. And then should I go X or Y next? Well, it doesn't make any difference.
Well, if you go X, it says 2 meters. Oh, but it's negative X. Oh, no, it's positive X.
So yeah, next I could go here. And then last I could go there. So I finally got where I'm going. This distance right here is 3 meters. Is it positive from here toward here? Notice the arrow. It's positive because that's a positive X right there. So that's a +3. And then I'm going this direction last, and that's a +Y, and that's a 2. So I went -6, +3, +2. But then I got to think, okay, now I got to get the order right. Because -6 is not X, so I can't put -6 first. So my X was +3, my Y was +2, my Z was -6. Notice you're using exactly the same numbers that you used last time, which means you're going to get the exact same hypotenuse, which is interesting. And also, it's just interesting to note that in this drawing, that's literally the length of the cable. Like those cables are 7 meters long.
So what did you say we were at the same? Same what?
The same hypotenuse, because you're going to be taking 2 squared plus 3 squared plus 6 squared. It's in a different order, but you're adding them, so the order doesn't matter. So you're going to get 7 for the hypotenuse again.
What does that mean?
That literally is the length. So literally because these are meters, from A to B is literally 7 meters long.
So they're the same length. Why are they just 2 separate locations?
Yeah, they're just 2 separate locations.
That makes sense. Looking at it. Is one, yeah.
Yeah, it's just one's 2 in the X and 3 in the Y, and then the other one's backwards, but it's the same exact numbers. But again, you can't really see that because it's 3D and you can't really tell which direction it's going.
So if you were to in your experience, think about this, do you think they're going to be the same force or do you think they're going to be different?
Yeah, and see, that's what's interesting is not necessarily because, if this, one time I took these bunch of kids to Mexico and we stood up this humongous, it's the biggest parachute you can buy. It's like the kind you drop Jeeps out of planes with and they don't crash on the ground. It's huge. In Mexico, it's super windy and you're burning to death. It was like this mission project. And we had a flagpole to stand up that was going to hold the top of the parachute. But it was really funny because we had like 10 kids on each rope to pull the thing up. But you have no way of knowing how hard you're pulling. And so basically you're pulling it up and everything is fine because everybody knows that if you're on the pull up side, you're pulling it up in the air. But once it gets to the top, now all of a sudden it's kind of like time for everybody to pull equally. Frankly, you should just be able to kind of stay there and chill and not really have to work that hard. But then there's a sense of like, oh my God, it's falling. And so you start pulling. But then what does the person on the other side do? Like, oh, it's falling. And then they start pulling. And then we're all like, ah, working our asses off. And it's just standing there. And so that's kind of true here. How hard does each one pull? Well, if somebody's at the bottom of it, however the heck hard they want to. Notice there's no force on this. It's kind of a weird problem because what are those doing there? They're actually only there in case the wind blows and it wants to fall over. If the wind blows directly away from one of the wires, then that one will have, the one behind it will have to work really hard. If the wind blows sideways to it, it won't have to work at all. So if you think of it as like a sail and a mast, it's a little better of an illustration, but they're not going to be the same because they're only going to react to the wind.
Right.
So watch this. So this time I'm going to be multiplying by 700, but if I just wrote this as a shortcut, would you understand what I'm doing? Isn't that what we're doing? I mean, I don't really care how you write it. And again, weren't they nice to pick 700? See why they chose that now? So the force of C as a vector is 300. I'll go ahead and write I's, J's, and K's. 300I plus 200J minus 600K. Now that these two vectors have been broken into their X, Y, Z components, it's extremely easy to add them. Force vector B plus force vector C. And again, it's kind of cool to write these vector symbols because it'd be awesome if we could somehow in 3D go grab one of those, because notice they're both tail to tail right now. If we could actually grab this vector right here and stick its tail at the end of this and then draw it in the same orientation, wouldn't it be something like this? If I drew this, wouldn't it look something like that? And then isn't this our resultant then from here to there? So I'm literally adding them. That's why it makes sense to write them as vectors like that. It's just the math version rather than the visual version. Yeah, notice the Z is massive. So all of that just to keep straight. So my force resultant then as a vector, I'm going to write it in this form. 300 plus 160 is 460. 200 and negative 240. Notice those are fighting against each other a lot. We only ended up with negative 40. Whereas the Z's are working together, man. Negative 600, negative 400, negative 1080. Here, if you've been lazy like me, you should stop being lazy and stick newtons on the end of this. Like, hey, those are all newtons. And that's still the X, Y, Z directions. And of course, you can see with respect to Z, yeah, they're both pulling down. They're working together to pull that thing down. So that kind of makes sense. Whereas one's pulling right, one's pulling left with respect to Y. So it makes sense why Y ended up like that. And they're both pulling in positive X, aren't they? I can see that. So that kind of makes sense. So again, we're done in one sense, but you could turn it into magnitude. I'm just going to write down the right answer to this.
So when I ask for coordinate,
Yeah, we'll do that one.
okay, coordinate direction angles, we have to figure out like this, which is just plugging them into that formula, right?
Yep. Now, stare a little closer at this answer here. Double check me if you want to in Pythagorean theorem yourself, that answer. What are you going to see in the back of the book? This is really important because if it's only going to report 3 numbers, that's not good because you can't just go 117 newtons. That's exactly right. So in order to get away with 3 numbers, you're going to have to go 10, 100,000 kilo. You're going to see 1.17 kilonewtons in the back. Again, don't change it. I don't care. But just look in the back and go, oh yeah, I got that right. Your first response is going to be like, oh no, I missed it. And then, oh no, I didn't. So I'll write some of these down. Alpha would be the inverse cosine of the x coordinate 460 divided by, and of course here you don't want to use 1.17, right? Because that's kilonewtons. You got to have the same units. So I need to use the 117. I don't care how you round it. 5, 4.6. I don't know. It doesn't matter. It's going to be pretty close either way. Typing that in, I get 66.9 degrees. One last shot at making sense of how confusing that is. If this is the x-axis on the floor, and I'm going to go 66 degrees from there, I could go 66 like that. I could go 66 like that. I could go 66 like that. I could go 66 over there in every single direction. Like that 66 is almost worthless at this point. Without the other ones, I have no idea where that's going. You can't even drive because we have no idea what direction it's going. We need all the rest of them. Because if I decide to go 66 from here, well, then automatically, what is that from there? Oh, it's supposed to be 40. So, okay, that's off. Now I got to move this somewhere else. I mean, it's really rough. Beta would be the inverse cosine of -40. I wonder what that's going to do, a tiny negative number over a really large positive number. Really close to 90. The inverse cosine of something really close to 0. Math this, just to stare at this for a second. This is the unit circle. Remember, cosine is the x coordinate. The cosine of an angle is an x coordinate. So this is your x coordinate, a tiny negative number. You agree with that? If you have a tiny negative x, doesn't that mean you're like right there? Where is right there? Right there. Oh, 92 degrees. Yeah, that kind of makes sense, doesn't it? A little past 90. No wonder it said 92. It's kind of cool to be able to think. This is the other reason I can't do this without iPads anymore. And of course, lastly, the inverse cosine of, ooh, huge number, -1080.
So is sine the only one that actually, I forget it, cosine.
Say it again.
Sine actually functions sometimes. You get two separate things on the.
Yeah, that's one of the reasons why this is kind of cool, because you only get,
Cosine doesn't mess with you.
yeah, cosine doesn't ever screw you up. Because yeah, in this picture over here, couldn't we also be right there and still have the same x coordinate? So isn't there sort of another answer to this? But notice what that answer would be. Wouldn't it be like 260 degrees? Well, you don't want to turn from something 260 degrees when you could just go the short way. That's kind of the idea. So fortunately, cosine, the answer it's giving you is the shortest path from the x-axis to that spot, or the shortest path from the y-axis. You could always go, if it's 92, you could say, no, I want to go backwards. I'm going to go 270. But that's dumb. So yeah, it's always going to give you the simplest, shortest answer, if you will.
One day I'll be smart enough to understand that. But right now I'm just like, sine's a bitch. I hate sine.
Yeah. What do you think?
Still kind of hard to wrap your brain around because I still picture. So this is why this is X. I'm thinking we're going 66.
Mm-hmm.
But then
So you've already assumed that you're staying in the flat plane with that,
exactly.
which
Because
you're,
I don't know. I can't picture in my head.
yeah, you can't.
Yeah. So you were saying.
Yeah. So the good thing about this is you can picture that it would be possible, but you know, it'd be kind of fun, if you will, to like have some long stick in the room that we could put in the corner and like brace it up there and then like start measuring it over here and over here and just keep moving it until it was all three of those. Like it could be done. Bring your own stick. He's got a giant protractor at home. But you can see that although the math of that method is preferable to the, and I probably would put a question like that on the test just because it's a little easier to draw and for you to see. Whereas if I do the azimuth transverse method, it's very possible the picture is going to be weird looking and kind of like, if it wasn't for the shading of that previous question, we probably wouldn't even have had a shot at understanding it.
So they don't use that in like real life, right? That method or whatever. It's mostly like what we just did.
No, it's both, I would say. Because see, the problem is somebody's got to build this. Like, if you were actually supposed to pull a rope in some certain direction and attach it, I'd rather be given that trick technique.
Yeah, what is this one called?
That's coordinate direction
I would
angles.
rather have that. So then I'm like, all right, I'm gonna walk 3 feet this way and then 4 feet that way.
Got it. And that's exactly why you very seldom see, and that's why this problem is in a sense better, because this is what you see in the real world. Not only can you figure out the forces on it, the resultant force, but you can actually tell exactly where everything goes because you're given distances, not angles. And so getting comfortable with this, as weird as this kind of feels, is kind of the key to this.
Yeah, if I was on the construction site and I saw all that shade and stuff, I was like, I'm gonna go mix some concrete. Let someone else deal with this.
Y'all tell me what to do later. I'm gonna go lay down over here. Let's do this really quick and then we'll get out of here. Let's see. Seems like there was a Blackboard login here. Okay. Am I logged in? No, I'm not. I don't know if any of you guys ever read anything in the Bible, but there's the whole thing in there about the mark of the beast and stuff at the end, and it's like scanning, but it's like all of these stupid. If there was a way to just have like your identity that you could just kind of go beep and then it would open, it's like, instead of remembering all these stupid. I'm afraid I would take that mark right now, even though
The convenience alone.
whatever it takes to make me not have to do this anymore. See, I just forgot it.
God's like, was it worth it? Was it worth it though?
Was it worth it? You got into your, it was worth it. See, because I'm on my third try now. Stupid password.
He goes to hell. He's got the finger on the way out. He's like, I do it again.
Anyway, we won't do it. I was just going to go into, have you got into Blackboard and kind of, because the notes that I'm posted in there is something you're probably going to want to look at some point to relook at things as far as your assignment. But and then also, you know, it's kind of tough to prepare you for the homework questions. As I said, what I try to do is pick the questions really carefully, the ones that I think are cool, ones that I think are good for you as a future engineer, and then I try to come up with some examples that are similar enough that you can kind of make the jump. So plan on walking in the door Tuesday with the first set of homeworks done. And to me, if you're handing it to me, I'm assuming that means you got them all right and you're happy. That's why I'm not going to look at them that much. Don't hand them to me wrong. Like, I am going to look at them. I'm going to give you points for each one. Because you handed it to me, I'm not just going to write points in the grade book. I'm going to go flip, flip, flip. And I'll probably look at like one of them carefully. But for the most part, it's going to be like, oh, they work. There's a bunch of work. Here's the conclusion. You know, there's the answer at the end, and then, oh, good job. That's all I'm going to. So make sure you're profiting from it, because this is not, this part of that part of your grade should be kind of a freebie. That doesn't make it easy, because you should have to ask me lots of questions as this class gets rougher and so forth. But in a sense, don't hand it to me until you're happy with it, is kind of what I'm getting at. If Tuesday you come in and you've got a couple of things that didn't work right, you know, email me and say, hey, can we meet early? And I'll show up here. We'll talk for 15 minutes and maybe I teach you a couple of things, and then it's like, okay, cool, hand it to me tomorrow. And then you go home and finish it. Great. That's what that's for. So ideally, I want all of your assignments, for your sake, not mine, to be 100%. And then you got a little room to screw up on the test and still pass the class. So good enough. This is one of the first times it's one of the few times you get out of here on time. So thank you all. Notice we're doing chapter 4 next. So if you're in a spot, it would be awesome if you could read, and I put this on the syllabus, reading 4.1 through 4.5. You'll get so much more out of next week's discussion if you read that ahead. Oh, this stuff is cool. I'm gonna start talking about it right now. Okay, why can't I log into Black?
Try capitalizing the key and password.
I'm not that old. Yes, I am.
See, though.